So we've looked at finding absolute max, absolute mins, local max, local mins. Now we're looking at applying these to some problems, and we're looking at applied optimization problems. So let's just go through the steps on how to solve these. First thing you want to do, and always want to do, right, is understand what they're asking us. So really, when I go through a word problem, I first read it. I might have to read it a couple of times, and then I start pulling out information that I know, and that is going to help me. So understand the problem. You're going to clearly identify what quantity is being maximized or minimized. And it's usually helpful if we can make a sketch of what's going on. So a lot of times we want to maximize or minimize something, but they're giving us information about other things about the problem. And these are usually constraints that we have, and it helps us to be able to take what we're maximizing or minimizing and be able to rewrite it in terms of one variable. So we're going to create equations relevant to the context of the problem using information given. So one of these should describe a quantity that we're trying to optimize, and we'll call this the fundamental equation. So just so that we're knowing what we're talking about, or whenever it's telling you maximize this area or minimize the cost, that's what we're going to call the fundamental equation, and that's what we're optimizing. If the fundamental equation defines the quantity to be optimized as a function of more than one variable, then we're going to reduce it to a single variable function using substitution derived from other equations. So I just mentioned that before. We need to identify the domain of the function, keeping in mind the context of the problem. Right, so if we're talking about area, or we're maximizing area, it doesn't make sense to have a negative length, right? Or so we just have to keep in context of what's going on when we're looking at our problem. We want to find extreme values of the function on the determined domain. And then we identify the values that are relevant to the quantities of the problem. Okay, so let's kind of jump in and just do one. So I want to kind of start a little simpler. Okay, so let's say that you want to find two numbers, or find the positive number. How about this? Whose sum of itself and its reciprocal is minimized, smallest as possible. That is a minimum. Okay, so let's think about this. We are trying to optimize that. If we maybe let x equal the number we're talking about. We know that x has to be greater than 0. And we're looking at minimizing, let's call it y. And we're minimizing the sum. So if we take x plus the reciprocal of x, which is 1 over x, we want to minimize this. So this is our fundamental equation. And we know our constraint is x is greater than 0. It's a positive number. Okay, so we know we need to take the derivative. Before we take the derivative, though, a lot of times we rewrite our function, so it just makes it easier to take the derivative, and I prefer not to use the quotient rule. I know I can rewrite 1 over x as x to the -1 power. So let's rewrite that function as y is equal to x plus x to the negative 1. So we want to find our critical values. We're going to take our derivative. So y prime is equal to 1. And then the derivative of x to the negative 1, that gives me minus x to the negative 2. So this is 1 minus 1 over x squared. Find critical values. We're looking at where this is undefined, but defined in our original, and where it's equal to 0. So let's look at where it's equal to 0. I have 1 minus 1 over x squared equals 0. So I can clear my fraction by multiplying both sides of my equation by x squared. And so doing that and distributing, we end up getting x squared minus 1 is equal to 0. So I can use the square root method here. I notice I can also factor here. So if we do this, let's factor it. X minus 1, x plus 1, we have a difference of squares. This equals 0. So either this is x equals 1 or x is equal to negative 1. But x equals negative 1 does not fall in this domain where x has to be a positive number. So this one doesn't work. And so we can see that x equals 1 looks like this is what it's going to minimize. We need to check this though. Does this really minimize this? Maybe we found a critical number that was a max. So we could do a couple different things. We can use our first derivative test and find where it's increasing, decreasing. But really that second derivative test is what will a lot of times be a lot faster. So recall, if we find that we have some critical number, C, I'm going to just kind of put over here, and we test it into the second derivative, and our value was greater than 0, I think of it as concavity, greater than 0 for second derivative, our function is concave up. It's a bowl that holds stuff. And so a minimum, this would be a min, then C is a min. Or a min occurs there. If we plug it in to our second derivative, and we find that the second derivative at C is less than 0, then we know that the parabola can't hold anything, shape, concave down, and there's going to be an absolute max at C. Not absolute, it's just a max. It could be absolute, but we don't have that. If it gave us 0, that didn't tell us anything, and we had to go back to the first derivative test. Okay, so let's look at taking the second derivative. So we have the first derivative, and taking the second derivative, I get derivative of my constant 1 is 0 is equal to, and the derivative of negative x to the negative 2 power. Well, if I bring down that negative power, that becomes positive 2, x to the negative 3 power. So notice if I plug in my critical number of 1, wherever I see an x here, this gives me 2 over 1 cubed, which is equal to 2, and that's greater than 0, which if it was greater than 0, we said that was going to be a min. So this is where it is a min. So a number that is positive, that if you summed it with itself and it's reciprocal, that the minimum that you could choose would be x equals 1. That would minimize that sum. So the next example, we're trying to maximize the volume We're creating a cardboard box that has a square base that will be open, and we're making it out of a 24-inch by 24-inch cardboard. And so if we look at this, we know that this is 24 inches in here. This is 24 inches in here. And we are going to cut a piece out of here on each corner. And we're trying to, once we cut that out, kind of think of it this way. Basically, if you cut those little corners out, you're kind of left with this shape in here. I'm not doing very well at drawing, and you're basically folding those flaps up so that it makes a box. Right. Okay, so you kind of get my idea, but again, I don't draw very good three-dimensional. I don't draw very good two-dimensionally. So you got this box here, and we know that that base, it tells us that it's square. Maybe we can call that X. So right here, that's telling me that this length in here is X. And this length in here is also X. And we know that this whole length of the cardboard is 24, but we've cut out some pieces. So, and we know that those are a square piece. Actually, let's call maybe, instead of the length there, X, let's maybe call this X. If we call that X, then I know what this side would be, because it's totally, the total side was 24. But if I take that 24 and I subtract off this X in here, minus this X in here, this would equal 24 minus 2X. So we know that this length in here is 24 minus 2X. And then we also need our height, because volume is equal to length times width times height. Well, that flap, that height we're using is actually X. So X is equal to the height. And so we can say that the equation that we want to maximize, our fundamental equation, is volume is length times width. Well, our length and our width are both 24 minus 2X. Times 24 minus 2X. All times the height, which is X. So we want to maximize this, maximize the volume. I could use the product rule multiple times to do this, or we can first expand. So let's first expand this out and then take the derivative. So let's look at 24 times 24. That's going to give us 576. 24 times negative 2x, that's a negative 48x. And then we have another minus 48x. So minus 48 times 2, that's going to give us negative 96x. And then we have a negative 2x times a negative 2x, which gives us a plus 4x squared. All times our x. So let's distribute that x so we get the volume. And I'm just going to rewrite mine in descending order of powers. It doesn't matter, but I'm going to. So 4x squared times x, we have 4x cubed minus 96x times x, so 96x squared plus 576. Okay, so let's maximize this or find the maximum that x has to be in our dimensions of the box and the maximum volume. So we're taking the derivative, we're finding our critical numbers. So the derivative of 4x cubed is 12x squared minus the derivative of 96x squared. So 96 times 2, that's 192. So minus 192x. And the derivative of 576 is 0. So we're looking at one is
be an x behind 576 because we're multiplying x across everything.
Oh, you are. Thank you. There we go. Yes. And so the derivative of 576 is 576. Oh, derivative of 576x is 576. So let's see if 12 goes into all those. So let's factor out a 12 while we're doing this. So we have x squared minus 12 goes into 192 16 times, so 16x, and 576 divided by 12, that gives us 48 plus 48 equals 0. So let's see if we can factor that. Are there two numbers that we can multiply to give us 48 and add to give us a negative 16? Well, 12 times 4 is 48, and 12 plus 4 is 16. So if they're both negative, x minus 4, x minus 12. And so if we look at this, we have x could either equal 4 or x could equal 12. In these problems, again, we have to think about domain. Would it make sense, and we don't have it here, but it wouldn't make sense that x is 0, because it would just be a flat box. Can't have volume there, right? But we can't have a number over 24, right? And that wouldn't make sense either. If we had x as 24, you're basically folding it up and there's no length or width. It's just folded box with no volume. And so here we have x equals 4 and x equals 12. So we want to maximize, and we want to see which one is a maximum. So let's look at this. We can either, let's just maybe look at it this way. So if this is 0 to 4 to 12 to 24. So if we chose something and we plugged it into our first derivative between 0 and 4 using the first derivative test, how about x equals 1? If I plug it into this first derivative, maybe let's look at it in the factored form. That way we can just look at, is it positive or negative? Well, if I plug 1 into x minus 4, that's going to be a negative number. And then if I plug in 1 into x minus 12, that's also going to be a negative number. So negative times negative which is greater than 0. So this is increasing. Let's look at what's happening between 4 and 12. So how about 5? Plug it in, 5 minus 4, that's positive, times 5 minus 12, which is negative. That's less than 0, so it's decreasing. So x equals 4, a max is occurring. But now look at this, how x equals 12 is probably going to be a min, right? If I plug in a number between 12 and 24, x equals 13. Yeah, 13 minus 4 is positive, 13 minus 12 is positive. That's going to be the derivative of 13 is greater than 0. So it looks like when x equals 4, is going to maximize the volume. It wants the dimensions, and so we can figure out what the base of the box is. So the base, or length and width, which is equal to 24 minus 2 times x, but x in our case is 4. So we have 24 minus 8, which is equal to 16. So our length is equal to our width, which is equal to 16 centimeters. And our height we found was equal to 4 centimeters. But it wants the max volume also. So our maximum volume would be equal to our length times width times height. So 16 times 16 times 4. So 16 squared times 4, which gives us 1,024 cubic centimeters. Questions on that one?